Okay, welcome to the screencast on Within Participants Anova. If you've seen the one on Between Participants Anova, you'll know that was a bit of a magnum opus and stretched to 3 parts, a real 3-part intervention. This is should be shorter and should be a bit simpler, because Within Participants Anova is a slightly simpler way to go about things. You don't have to have any splitting files and things like that. It's a bit simpler apart from one little bit where there's a little wrinkly, difficult get your head around it bit, but once you get over that, everything's fairly straightforward. The task we've got here is participants are performing a task, and the task they perform is either simple or complex, and they're performing it either in quiet conditions or noisy conditions. So we've got a 2x2 design, 2 variables, each with 2 levels. Variable 1 is task complexity, where it's a 1 is simple task and level 2 is the more complex task. Variable 2 is noisiness, and level 1 of that would be quiet, and level 2 of that would be noisy. So we've got the data entered in here: simple, quiet, simple, noisy, complex, quiet, and complex, noisy. And you can see here, this is a perfectly within participants' design. If we consider the columns to be measurements taken of a person and the rows to be people, then participant 1 takes part in all 4 conditions. So that's relatively straightforward there. First thing you would do when you once you've entered this data correctly is to do a test for outliers, and then a test for normality, skewness, before you do anything, before you get descriptive statistics out, because the decision about which descriptive statistics you use, whether you use means, medians or modes, is partly dependent upon whether the data are or are not skewed. If the data are skewed, then you shouldn't really use the mean, significantly skewed that is, because it becomes less representative of the typical person's score. You should use something like a median, because the extreme scores for in skewed data drag the mean up or down depending on whether the extreme scores are towards the high end or the low end, and make it unrepresentative. That's why you're not also shouldn't do t-tests. And others on skewed data, you either have to do a non-parametric equivalent or transform the data using some form of transformation algorithm, such as finding the reciprocal of the data, square root of the data, squaring the data, or finding the logarithm of the data. I discussed this in the lecture when you did in study week in October. So we've got the 4 conditions here. So the most important thing here is to think in terms of variables rather than conditions. So let's go and find where the ANOVA is. It's again in general linear model, which is, you know, the very transparent way that SPSS signals to you where things are by giving you very transparent little labels, so you immediately know where things are. Fortunately, it's in repeated measures, so we can see that there. I've already done this in a previous example, but let's start again. So we've got within subject's factor name. Now again, think variables rather than conditions. It's very easy at this point to kind of run away with yourself and go, yeah, there's 4 conditions, and enter one factor with 4 different levels. Well, we've not got one factor with 4 levels. We've got 2 factors, each with 2 levels, or variables. So the first one, let's call it complexity. I could call it simplicity, but who cares? That has 2 levels: simple, complex. Click add. Second one is noisiness, and again that has 2 levels: quiet and noisy. We click add. So we've got both of our variables in here. Now we need to tell it where the levels are. So we've got to click on define. Now this can be relatively straightforward, but it's worth checking, because I've seen students enter the data here incorrectly. If you look in this right window here, we have 2 little spaces with a question mark between them. This is where we're going to put the variables. But what we need to make sure is that they all match up. So you see here it says 1, 1. So the first number is the variable number, and the second number, the numbers correspond, the ordinal position of the numbers correspond to the variable. So the first number here will be variable 1, and the second number is variable 2, and the value of the numbers is the level of that variable. Okay, so 1, 2 simply means level 1 of variable 1, and variable 1 is complexity, and level 1 of complexity is simple. Level 2 of the variable complexity is complex. Okay. Doesn't matter which way around you get these necessarily, as long as you're completely consistent. As long as 1 always means 1 and 2 always means 2, then it's fine. There's nothing magical about it, but you just need to be consistent. So level 1 of variable 1 is simple, and level 1 of variable 2 is quiet. Simple, quiet. So that's the one there. So the next one asks us for level 1 of variable 1 and level 2 of variable 2. So we know that level 1 of variable 1 is simple because we've already done that one. So level 2 of variable 2 must be noisy. So that's the second one there. These actually do go in order, but sometimes they don't. Don't expect us to plonk them in 1, 2, 3, 4. Sometimes you have to think it through. Level 2 of variable 1 is obviously complex because 1 is simple, and level 1 of variable 2 we already know is quiet. So complex and quiet, that's good. And level 2 of variable 2, sorry, level 2 of variable 1 is complex, and level 2 of variable 2 is noisy. So we've got all those in there. But as I say, we need to make sure that all the 1s match up with the conditions, and the 2s as well. So we want to get some options here. So let's have a little look at what options we might want. We might want descriptive statistics. We can display means for the complexity and noisiness, which will help you for the tables and things like that. It's an easy way of getting the stuff out. Let's do some homogeneity tests. Estimates of effect size are always useful as well. There might be other things. You might want to do power. I don't think this is terribly helpful all the time if you report an effect size, but it might be something you want to pull out later and explore, but let's keep that under wraps for the moment. So we do continue. Plots might be nice. Complexity and noisiness. If you've seen me talking about the between participants ANOVA, I do these both ways round. So complexity times noisiness, and then noisiness times complexity. Click add. Because sometimes you don't know which graph is going to be most meaningful. And graphs give information, different graphs, different ways of representing the same data can give you different things and can be easier to interpret. So get as much information as you can. There are no between subjects factors. It's not a mixed design, it's a within subjects design. So we can click on OK here. Now what I've been suggesting before is if you go to the, first of all go to the graph, and we can try and see what's going on here. So this is complexity. So if we take the noisy tasks, so the quiet task, variable 1 of the noisy condition. Okay, this is noisy, simple. This is a noisy, the quiet task, not the noisy task. We can see that doesn't seem to be any difference in this blue line between 1 and 2. So there's no effect, it seems, of complexity on task performance when the task is simple. Okay. Now, big is bad. The dependent variable here is how many errors were made. Okay, I may not have mentioned that, but that's what it means. So the bigger the number, the more errors were made on performing the task. So there's no more errors on a simple task for this, for the noisy condition and the non-noisy condition. But if we look at the complex task, then we can see that there are more errors made in the complex task here too than there were made in the simple task. Now, I can't stress this enough. Once you've got the output, have a look at a graph. Right? Before you look at the ANOVA, try and tell yourself a story. Try and interpret the data looking at the graph. If this graph doesn't work, then maybe this one will help. I don't think this is quite so clear cut because this looks at complexity. But you can see here that a complex task, there's not really any difference between 1 and 2. There might be a slight difference. It's dropping a little bit between this is noise. This is quiet and this is noisy. But for the complex task, the performance is much worse under the noisy condition than the quiet condition. So this one to me doesn't quite communicate it as simple as that. I can understand this one more. That's why I suggest 2. Find what works. Find what works with your head. Okay, so we're predicting there that we might have. We don't really know about main effects. There may be a main effect of complexity, but certainly there appears to be an interaction here. If you've seen the between participants and one, the interaction isn't as marked. Where that one was a pure crossover interaction, where we've almost like an X drawn on the mind. This is a bit of a crossover because you can see that performance on the complex task, the number of errors made is slightly lower than performance on the simple task. But it might not be significant. So let's go and have a look at the ANOVA. So let's go right to the top here. So this first things aren't terribly interesting. This just tells us what our variables are. We've already discussed that. This is our the means for each of the conditions, which again is not terribly useful because these conditions are comprise two variables. So what we have here, let's have a look at this. This is a thing called Morchley's test for sphericity. A way of thinking about this is it's a bit like Levene's test for the equality of variances, which we've looked at both in ANOVA and in the independent samples t-test. One of the things that ANOVA likes is for the variation in each of the groups, the standard deviation or the variance in each of the groups to be about the same. It doesn't like it when one group is kind of got quite a lot of spread and the other groups have got comparatively little spread. So this is a test for that kind of thing. It's not exactly that, but just think of it that way and you won't go far wrong. Morchley's test tests whether it's significant. If this is non-significant, then we can assume that sphericity is okay, right? So we scroll down now to our within subjects effects, which is where our data are. We can see that there's a main effect of complexity here. There's a main effect of noisiness here. And there's a significant interaction, as we might have anticipated, a very big one as it turns out. If we look at our partial eta squared values here, they are really quite large. Talking about sphericity, if we can't assume sphericity, which is like equality of variance, we can't assume it, in other words, Morchley's test is significant, then we could not read across this top one here, sphericity assumed, because we can't assume it. We would instead probably read the second one, the greenhouse geyser, there, which is exactly the same in this instance. But if we couldn't assume sphericity, you would find that greenhouse geyser would be a different number, just sphericity assumed. So we can assume sphericity because the test is fine. So we found two significant main effects and a significant interaction, so we could report that. Okay. Next thing to do is our simple main effects. So we want to look at our pairwise comparison t-tests. Now, we don't need, let's go back to the data here, we don't need to split the file in this case, because splitting a file is when you've got coding variables. We don't have coding variables. So what we need to do here is just do some paired samples t-tests. So let's go to Analyze, Compare Means, Paired Samples t-tests, and all we do, we need to do all these against each other. So simple quiet, simple noisy, simple quiet, complex noisy, simple quiet, sorry, complex quiet, simple, complex noisy, and the final one would be these two. So these are all the four possible pairwise comparisons. So simple, yeah. And what we find here, again the t-tests here, paired sample t-tests here, we find that there's no difference between simple quiet and simple noisy. There's no difference between simple quiet and complex quiet. Remember, that was where the blue line was perfectly flat. It's actually basically the same number. For simple quiet and complex quiet is the same number, which we've got a significance of 1 and a t of nothing, because there's no distance in there at all. But there is a significant difference between simple quiet and complex noisy. So that's the only significant difference. So even though we've got a main effect of something, even though we've got two main effects in an interaction, the actual only significant pairwise t-test here is between simple quiet and complex noisy. That is the green line that shot up in the air, if you remember from the previous one. We'll go up and have a look at that in a second. So remember also that we need to do a Bonferroni correction here, because we've done 4 pairwise comparisons, so we need to divide 0.05 by 4, which is from memory something like p is less than 0.00125 or something like that. So as long as this number here is less than that, we can say it is significant. And it is. The real number is 0.00030 zeros and 8. So it's actually less than 0.00125. Sorry, 0.125, not 0.00125. Let's make that clear again, that the Bonferroni correction is 0.05 divided by 4, which is 0.0125. 125, 0.00. Okay.